Good morning, everyone. This is Shauna, and I'm here today to do a walkthrough a little bit of section 7.1. This marks, hold on, this marks a bit of a departure from some of our previous work. We're going to get into something called estimations. And so we're going to be looking at a concept called the confidence interval. I'm going to bring up the screen here in a moment. I can get my Zoom to cooperate with me here. So, as I said, this chapter is about estimations, and it's confidence intervals. The whole chapter is on confidence intervals. The first section that we're going to be looking at is confidence intervals for the mean when sigma is known. And that's going to be a Z as in zebra interval. Okay. We have our usual math common phrases here. Now, there's a couple of ways to make an estimate if you think about it. I can say something like, I estimate that the average age of Cerritos College students is 25. I can give you a single number based on that sample. That single number is called a point estimate. Okay, so we have two types of estimates that we're going to be dealing with. By and large, we're going to be dealing with the second one, but I wanted to make sure that you understood that there's two kinds. And so we have what we call the point estimate, which is always a single value, okay? And it's based on a single value from the sample data. And then we have what we call the interval estimate or the confidence interval. So here we have something like, oops. We have the confidence interval. And that is a range of values. So this is the difference between saying something like I estimate that the average age of students at Cerritos College is 25 years, right? That's what we call a point estimate. This is a point estimate. Versus, I can say something like this. I can say, I estimate that the average age of Cerritos College students is between 22 and 35 with 95% confidence. We're going to talk more about the elements of these in a minute, but I just wanted you to understand the difference between a point estimate, which is this first one on the left, and a confidence interval estimate, which is this one on the right. And we have different confidence intervals depending on what our parameter is, whether we're estimating a mean or proportion or standard deviation or something else. Now we have two confidence intervals for the mean, two different types of confidence intervals for the mean. And so I'm going to go ahead and go back to this. So there's a section in the book where it asks you about the best point estimate for the mean, the best point estimate for the standard deviation, that kind of thing. So this first slide just goes over what I told you. The important thing to remember too about an interval estimate is that the interval that I choose may or may not actually contain what the average is. It always contains an average, but it may or may not contain the true value. We don't know that. That's why we're estimating it with a certain percentage of confidence. Okay, let's continue here. I'm going to continue with some other definitions. We talk about, okay, I'm going to get into that later. And then, okay, we're going to talk about marginal error. So I'm going to show you some stuff with some of these examples. Let me put up the homework at this point and show you what the homework for this section looks like. So the first thing to note is that I need to share a different screen. Okay, here we go. What is the difference between a point estimate and an interval estimate of a parameter? Which is better and why? I just gave you the difference between a point estimate and an interval estimate. Generally, an interval estimate will be better because it takes in more data, but it also carries with it a measure of how confident you are in whether or not the true value is in your interval or not. Okay. So that's that situation. These first three questions come from the book. What is the margin of error? Now, to explain to you what the margin of error is, I probably need to show you a confidence interval first. So what I'm going to do here is I'm going to stop sharing this. And I'm going to pause here. Okay, now if you recall, we left off with the properties. I'm sorry, we left off with the margin of error and the properties of a good estimator. So let me show you where that's at. These are not on the slides. This is in your textbook, but let me give them to you. Let me show you where they are. So here, I'm going to go to this book. Let me make sure I'm sharing the book here. Okay. So I'm going to come back to the margin of error in a second. I'm going to actually take you to, this is a confidence interval and they break it down, but I'm actually going to take you to an actual confidence interval so you can see this. So let me look at this problem here. This is an example of a calculation of a confidence interval. You see at the bottom, we have 54 minus 1.7. I'm reading in the middle right here. I'm reading here. So this is where I'm at. Oops, right here. 54 minus 1.7 is less than mu, which is the mean, is less than 54 plus 1.7. That 1.7 is your margin of error. The 54 is our sample mean X bar. We'll get into this more in a minute, but that margin of error is a measure of how much distance there is between my sample mean estimate and the actual population mean. So it's a measure of how good my interval is, how narrow it is, and how well it approximates the population mean. Now let me show you this, because if we're looking for the actual definition of this, you'll find that down here at the bottom of page 372, and that's where your definition is. It says, the margin of error, also called the maximum error of the estimate, is the maximum likely difference between the point estimate. Remember, that's your single value. In this case, it would be the sample mean of a parameter. So we're estimating the population mean and the actual value of the parameter. So the population mean has an actual value. We estimate the sample mean to be something, and the difference between the two essentially is our margin of error. There's a calculation for that, but this is the definition of the margin of error. Now, the next thing the homework asks you are the properties of a good estimator. So how do I know that the sample mean is a good estimate of the population mean, or that the sample standard deviation is the best point estimate of the population standard deviation? Well, the book tells me, but there are properties for it. And those properties are listed on the next page. So if you're looking for the next page of this, the next page gives you the properties of the unbiased estimator. So let me get you that. So where we left off talking about properties of a good estimator. And so let me show you that, because that's actually from the book. They're up here in this blue box. So the estimator should be unbiased, should be an unbiased estimator. So the expected value of the mean, or whatever the parameter that you're estimating, obtained from the samples is equal to the parameter being estimated. In other words, another way to say this is that if your estimator is unbiased, your sample is a good representation, a good mirror of the population. Because think about it, if your sample mirrors the population really well, then your sample mean, the mean of your sample, should reflect the mean of the entire population, and they should be close. That's what we mean by an unbiased estimator. The second point is that the estimator should be consistent. So if you take confidence intervals repeatedly with a larger sample size, okay, remember, as the sample size gets larger, you're taking in more of the values from the population. So you should be getting closer, in theory, to what the real mean or the real standard deviation, or whatever the parameter is that you're estimating. You should be getting closer to the value of the population parameter as you increase the sample size. And it should be relatively efficient, okay? So you could use other ways to measure whatever this is, the mean or the variance or whatever. But your efficiency means that your estimate has the least variance, the least amount of wiggle room, so to speak, in that. So these are the three properties. They're unbiased, it's consistent, and it's relatively efficient, okay? These are the properties. I'll go ahead and leave this on the screen. Go ahead and take a screenshot of this if you need to, or stop the video. But I'm going to go ahead and have this disappear in 4, 3, 2, 1. Okay, now we've answered all of the sort of comprehension questions. There's another piece to this. Let me show you the slides here. I'm going to continue forward with our slide presentation now to the real parts of this. And I'm going to make sure that I'm sharing the slides. Okay, so now I'm going to show you the actual formula. This formula is your formula when you're estimating a mean with sigma known or n greater than 30. This is the formula here. Now, it looks hairier than it actually is, because if you look closely at this formula, you'll see that this part, this z of alpha 2 sigma over the square root of n, is repeated on both sides. We've got mu. Mu is the population mean here. This is what we're trying to estimate, okay? Mu is the population mean. Sigma, I'm sorry, x bar is the sample mean here. And this z of alpha to sigma over the square root of n, we're going to go over that. This z of alpha 2 is what's called a confidence coefficient. This changes depending on the level of confidence that you want to achieve. The sigma and the n, the sigma is the population standard deviation that will have to be given to you, or you'll have data that give it to you. And then you'll have the square root of the sample size, which will also be given to you, okay? These z's correspond to specific confidence levels, okay? And we'll talk about more where that comes from in a minute. The standard error, this is a little bit different. The standard error is this quantity in parentheses, sigma over the square root of n. You can think of that more or less as the kind of the standard deviation in this case. It's a multiple of the standard deviation. It's divided by the square root of the sample size. The marginal error, we went over. The marginal error is the error, the space between your actual estimate and what the actual parameter is. And that just includes this confidence coefficient, okay? So just a little bit of terminology here. Don't get them mixed up. Standard error, quantity in parentheses. Marginal error includes the z. So it's the z times the standard error, okay? The next thing here is we're going to look at so here's your issue. Now, I'm going to take you through some of this. We're going to look for the confidence coefficients next. This will bring us to question 4, okay? And I'm going to do one part of question 4 for you. This is your procedure for finding it. There's also a separate handout that has all of the confidence coefficient procedures on it. Okay, but this is in the slide for your convenience. Find alpha, find the area from negative infinity to the z alpha 2 line, which is 1 minus alpha over 2. And then we're going to use our inverse norm command, which you've seen before, and round to 2 decimal places. So how does this work? Okay, find the z of alpha 2 for a 98% confidence level. Okay, so let me show you what's happening here. Here she did the math, okay? So let me show you something here. So this is going to be how it looks. Let me go to the whiteboard. And we're going to look at this. I'm going to draw a distribution, okay? And we're going to put some stuff in the distribution. So let's just say now, the one thing about this is, you know, from your previous study that you have two z-scores, right? And you have two sides because our confidence interval is going to have two parts, a lower bound or a left side and a right side. And we're going to have area in the tails being the small parts of this distribution that are symmetrical, okay? But in this case, what we're going to do is we're going to start with alpha. Now, alpha is going to become very important for us in this chapter, and particularly the next chapter. But alpha, which is that curlicue kind of looking thing, alpha, that's always 1 minus whatever the confidence level is, okay, as a decimal. So if we're looking for, so the instructions here said on the slide, it said look for the confidence coefficient at 98. So what we're going to do is we're going to say, okay, we want to find the confidence coefficient for 98% level. So what we're going to do is we're going to say this. We're going to start with the idea that we have 1 minus, and I'm going to use the decimal, okay? 1 minus 0.98. Okay, now that's 98. That's going to give us, remember, 1.00 minus 0.98. This is like $1 minus 98 cents. This is going to give us 0.02. Okay, 0.02. If you need help to do this on a calculator, by all means, do so. This is 0.02. This is my alpha. Now, my alpha is my total tail area. So this is my area in both tails, okay? So this is my area in both tails, okay? I don't want the area in both tails, and I'll explain why in just a minute. So here, this piece now is 98. This is where we are in the middle. This is 98%, okay? We need the area in this, but we need to split this alpha. So what we want is, we always want, the other thing to know is that when we are looking for a confidence coefficient, and this applies to z's and t's are coming in the next section, we want positive values, okay? We want a positive z. So we know it's going to be repeated over here on the left, and it's going to be negative. we want this Z. This is the one that we want. This is our Z of alpha 2. Now, this is our Z of alpha 2. And I didn't do a very good job. Let me see if I can find my eraser. Is not working well. But this is my Z of alpha 2. Anyway, what I'm going to do is I'm going to go ahead and these values here, this is half of 0.02. So these are 0.02 divided by 2, which is where she's getting her alpha over 2 idea from the other slide. Okay, this is 0.02 divided by 2. So then, now, remember when we put it in the calculator, we need to determine our area to the left. So what we're going to do is we're going to use this idea of 1 minus this whole thing on the right. We want 0.02 divided by 2 and 98. So what we're going to do is we're going to employ the complement. So when we do this, let me come back to the shared screen here. And let me show you what we're doing. So this is 1 minus 0.02 divided by 2. And I'm going to put this in my calculator just like it is. It will evaluate this for me, okay? It will evaluate it. So what I'm going to do now is show you that. I'm going to say that here's my, give me a moment. Let me see. We're going to go ahead and open up the calculator here and share the screen. So now this becomes, now, where do you find inverse norm? Well, if you remember from the last section, that's second distribution, second vars. Number 3 is what we're going to use for 7.1. Okay, 7.1 is going to require inverse norm. And we're going to put in 1 minus, use the big minus. This is not a negative number. 1 minus. Alpha, remember, is 1 minus the confidence level, which we decided was 0.02 divided by 2. Enter it. Leave your mean and your sigma on 0 and 1 because we're looking for the z-score. And paste it, and then enter. 2 point, and we're going to round this to 2 decimal places. So this is 2.326. This rounds to 2.33. Okay. So this procedure on this slide, excuse me, the procedure on this slide is what you're going to use when you're finding confidence coefficients, okay? And that's going to match, if you look carefully, that's going to match with what you're doing with the homework for question 4. So let me show you that. Here's my homework. Oops. So we've got this. Let me share the screen. So this is our homework for that. So you're going to, now that example, that matches 4B. So example 1 matches 4B. So I'm not going to do another example. She did number 4B on example 1. And if you go down, you can see that 4B was 2.33. Okay. So I'm not going to do another example of that for number 4 because she did it for you here. Okay, I will do an example. I'll do number 5 here. Okay, so number 5 says, since 1975, the average fuel efficiency of U.S. cars and light trucks, SUVs, has increased from 13.5 to 25.8 miles per gallon, an increase of over 90%. Okay, so we know we're trying to find the average. We know that. This doesn't help me much other than it kind of gives me a rough interval back in 1975, but it doesn't really tell me what I'm supposed to do now. But when I get to this part here, it says, so here's my issue. It says a random sample of 40. Okay, that's my first big piece of information. A random sample of 40. This 40 is my n. So what I'm going to do here is I know that this means that n is 40. That's what that means. A random sample of 40. From a large community, got a mean mileage of 28.1 miles per gallon per vehicle. So each vehicle averaged about this amount. Now, this happens a lot in problems that are going to come up. You have a mean here, okay? Which mean is this? Is this the population mean or is this the sample mean? Well, it goes with the sample. A random sample got a mean. So this has to be your sample mean here because it refers back to this, a random sample of 40, okay? Has a mean mileage of 28.1. So here we have X bar, and remember I use X bar for my sample mean. So X bar here is going to be 28.1, okay? 28.1. So now it says the population standard deviation. And remember in this section, you have to know that. The population standard deviation, what's that? That's sigma. Sigma is my population standard deviation. Now, some of you might be saying, wait a minute, I thought sigma was that E looking thing. It is. This sigma that means the sum is a capital sigma. So it's an uppercase sigma. The sigma that looks like a 0 with a line over it is a lowercase sigma, okay? They're both sigma. One is lowercase, one is uppercase, context is going to help you figure it out. But this lowercase sigma, this O with a line over it, is the lowercase sigma. The population standard deviation is 4.7 miles per gallon. So sigma here is 4.7. Okay. Now, the only thing we don't have is the confidence coefficient. Okay. Estimate the true mean. So we're estimating mu. Okay. We're estimating mu with 95% confidence. 95. Now, if you do number C, 4C, if you do 4C, you can use that Z value down here, okay? So the Z value for the 95% confidence interval is from 4C. So do that, do yourself a favor. And if you don't have those numbers or you don't have them memorized, you can follow the procedure in the slides. I'm going to tell you that the Z here, my Z of alpha 2, just for expeditiousness, just so we can get through this a little faster, Z of alpha 2 is going to be 1.96, okay? So for any confidence interval that you do involving Z's with 95% confidence, Z is going to be 1.96 to 2 decimal places, okay? If you happen to be using the charts, you'll have to average two numbers out and you go with the higher one, and this is going to be your Z. So these are my values, okay? N is 40, X bar is 28.1, sigma is 4.7, and Z of alpha 2 is 1.96. We're going to put this in and we're going to find the confidence interval, okay? So I want you to write the numbers down that you see on the screen. I'm going to write them down myself here. And then we're going to find our confidence coefficient, our confidence interval. So X bar is 28.1. N is 40. Z is 1.96. And sigma is 4.7. Okay. So now we're actually going to construct our confidence interval. So I'm going to go back here. This is going to disappear in 3, 2, 1. Now I'm going to come back here, go to my whiteboard, and we're going to do your confidence interval. So when you have a confidence interval, as we saw briefly before, we have mu in the middle, okay? Then we have this thing on both sides of it. And the thing that we have on both sides of it is X bar. This is going to be minus Z with a subscript of alpha over 2. I'm going to do my best to draw. And then you're going to multiply that by sigma divided by the square root of n. Okay. Sigma divided by the square root of n. And over here, you get X bar plus sigma divided by the square root of n. Now, we have our values. We're going to plug it in. Oops, and I'm forgetting my z. Hold on. This is z alpha over 2 times sigma over the square root of n. So this is sigma alpha over 2. It looks like 4, but it's supposed to be alpha. I'm having issues with my pen right now. X bar plus z times sigma over the square root of n. Now, remember this is called the standard error. Okay. And this with the z attached is called the margin of error or the marginal error. Okay. So what usually is easier to do is to calculate this and then add the mean or subtract the mean to it. So I'm going to go ahead and put this in the calculator here for you to see it. So this is going to be, let me write the numbers out. So this is going to be, my X bar was 28.1. So I have 28.1. And actually, before I do that, I'm going to get us a new page here, because I'm going to say that X bar, I'm going to write this out, X bar is 28.1. N is 40. Sigma was 4.7. And my Z was 1.96. Okay, I didn't go through finding it, but I gave you an example of how to find it. My Z of alpha 2 here is 1.96. So now, those are my values. What I'm going to do is I'm going to go ahead and put them in the following way. So now, usually what people find easier to do is to calculate the margin of error first. So I'm going to write ME for margin of error here. Okay, margin of error. And that's going to give us, this is going to give us, this is, I don't know what's going on with my pen right now, but that's my margin of error. This is going to be Z sub alpha over 2 times sigma divided by the square root of n. So here I get we're going to plug all this in. So we have, this is going to equal, this is going to be 1.96 times sigma, which is 4.7. There's my decimal where. over the square root of 40. Okay. So this is going to give me my margin of error for this part. And then just going to form my confidence interval. Usually margin of error we take to 4 places. So what I'm going to do is bring up the calculator here and show you this. So we have 1.96, oops, 1.96 times parenthesis 4.7 divided by the square root of 40. Okay. And that margin of error is going to be the same on both sides. So it's 1.4565. And so now, if you remember, my X bar was 28.1. So what I'm going to do is I'm going to have this. I'm going to have my confidence interval here is going to be, I'll fix the calculator in a minute, but this is going to be my X bar, which is 28.1 minus my error, which is this number that you see on the screen, 1 point minus 1.4565. And that's going to be less than mu. I'm going to use U because I'm on Zoom, is less than 28.1 plus 1.4565. I'm going to go ahead and spew that out. This is my numbers when I plug everything in. So just to remind you, this is X bar here. This is the margin of error that I calculated. So this number is my Z alpha 2 times sigma over the square root of n. So this was my answer here. This was what this answer was on the previous screen. Okay, when I plugged in my numbers, that's what I got. And it's the same thing over here, except that I'm adding it. So the one on the left should be lower, less than your mean, your sample mean. The other one should be higher. You should have one that's lower, one that's higher, and mu should be in the middle of that. So let's take a look. Let's do the calculation. Let's come back to the calculator now. And let's look at my interval. So this is 28.1 minus 28.1 minus this answer. So I'm going to take my answer there, and I'm actually going to no, because I want to round it. 28.1 minus 1.4565. So 1.4565. This is going to give me 26.6435. All I'm going to do, a little bit of a shortcut, I'm going to go up here, grab my number, hit enter, and all I'm going to do is use the arrows to go back and change this minus to a plus sign. So my interval now is this. My final answer looks like this. It's 26.6435 is less than mu, is less than 29.5565. These are my values. This is 95%. Now, if I change the Z to 98 or 99, what's going to happen is those boundaries, if you think about the normal curve, they're going to push out. So it's going to be a wider interval. So if I make the confidence level larger, like 99, for example, these would be different numbers and there would be more distance between them. Okay, it would be a wider interval. Okay, if I were to make this confidence interval lower, like say 90%, okay, then what would happen is the numbers would be a little bit closer together, but I'd have a larger chance of not actually having the true mean in the interval itself. So let's go back 26.6435 to 29.5565. Let me show you that was number 5 that we deconstructed. So what I'm going to do is I'm going to erase my annotations from the screen. As long as I can actually do so. Let's see. I'm going to stop sharing it and come back. Share screen. And this was my so if I come down, you can see that she rounded here to 1 decimal place. So 26.6 to 29.6. Usually she rounds to 4. So the key, you may have slightly different answers than the key, but just know that in the key, she rounds to 1 decimal, but the Z's are all 2 decimal points. Okay. So that pretty much covers the confidence interval. Now, we have one more thing in this section, and that is, let me scroll down. I'm just going to show you an example of this. So she gives you raw data. You can read example 2 on your own. The difference here is that you're going to have to get when you put it in, you're going to have to get the Z for yourself if it's not one that you've already calculated. Okay. So this is pretty much how that works. I'm going to talk to you about the minimum sample size. Sometimes, as researchers, if you're doing this as a career, you want to know how large a sample do I need so that my confidence interval has a certain amount of error built into it. right? I don't necessarily know how many subjects I'm going to need. I would like to know that. What they do, you don't have to derive this formula. It's on your formula sheet. But basically, if you remember the formula for standard error, the z sub alpha 2 times sigma over the square root of n is equal to the error term. This marginal error is your E now. What they've done is they've solved that for your sample size, and they've rearranged it. Whoops. They've rearranged it and given you n. Okay. So you have your Z, that's going to come from your confidence level. Remember, indirectly, right? It's going to come from your alpha. You're going to do the steps that we talked about. Sigma will be given to you, and it'll tell you within a certain amount what you want. You're just going to plug it in. Now, I'm just going to show you an example from the slide. So it is desired to estimate the mean, so we're estimating a mean, number of chocolate chips per cookie for a large national brand. How many cookies? How many cookies? Not what is the mean, how many cookies do we need? How many cookies in the sample? What is my N? To estimate the mean. Why is that important? Because later on, we're going to learn to estimate other things. That's why this is highlighted. The mean number of chips within 2 cookies with 95% confidence. Assume that sigma is 10.1 chips. Now, this within 2, that's my error. Okay, within however much is my error. 95% confidence, remember, leads you to a z-score of 1.96. If you don't remember, or if you're given a confidence level for which you don't have the z-score, you have to do that process like you do in problem 4 and find it. But 95 is used quite a lot. So what we do, here's my formula. N is equal to z alpha over 2 times sigma over E, quantity squared, okay? She goes through the Z formula for you, okay? I did that earlier. I'm not going to do that again, but she goes through the calculation. I showed you the rationale behind it. Your Z is 1.96. Your sigma is given as 10.1. Your error is within 2 chips. So error is 2 here. You're going to square the entire fraction. So you just put it in the calculator just like it is. 1.96 times 10.1 divide by 2. Put parenthesis around it, square the whole thing. You come out with 97.9704. Now, for sample space for sample size calculations, regardless of what the parameter is, sample sizes are always whole. I can't have 97.97 people or cookies in this case, because I need a full cookie for part of my sample. So your sample size, when you're doing this, is always a whole number. Now, regardless of where this ends up, if this had been, say, $97.23, whatever this was, you would round up here, okay? You would round up because you need 97 and a little more. So it doesn't matter how far over or under you are. If you get 97, whatever number, point anything, 0.003, take it up by 1, okay? Your sample size should always be a whole number, okay? And it's always that formula when you're estimating with a mean with sigma known. Okay, those are the last problems of the section. That covers, let me show you one more time. This is going to cover the last 3 problems, 11, 12, and 13, on your homework. Problems 11, 12, and 13 have to do with sample size calculations, okay? The others are confidence intervals, okay? The last 3 are sample size calculations. That was just meant to give you an overview, a little bit of a talk through, and I hope it's been helpful to you. I trust that I'll see you very soon. In my next video, there is additional embedded tutoring support for this section, so I will post those videos, but start with this video first before you watch those, because they assume that you know something already about what's coming up. The next section, we're going to do something very similar to this, but we're going to use a new distribution that's very similar called the T distribution, T for Thomas. And it's similar procedures, but it involves a little bit of a different distribution. So we have some different properties for that. But that's about it from here, folks, for now. I hope that you've enjoyed this video. Hope that you've learned something, and I'll see you very soon. Take care and bye for now.